Hi everyone, Dr. Manis here, wrapping up our discussion about gas laws in this final video where we just do a couple of extra problems on gases based upon kinetic energy, velocity, and Graham's law. These are concepts commonly covered in AP classes or first semester college classes, not so common for your first year high school classes. But anyway, kinetic energy is just going to be 3 halves RT. Alrighty, you may know kinetic energy more commonly if you learned it in physics class. Kinetic energy is 1/2 mass velocity squared. And that's all well and good, and that's true. But once you can do a lot between those two terms and convert things over using gas laws and get to 3 halves RT. 3 halves RT basically means kinetic energy is independent upon the amount of the gas or the type of the gas. Kinetic energy is just dependent upon the temperature. It's an average because you got a lot of particles and they're all going to be exactly the same. So we take an average. Don't forget the temperature has to be in Kelvin. And because we're dealing with energy, that little puppy down there, that better be in joules. You got to use the R value that gives you joules, and so that's 8.314. As a quick example, let's look at the kinetic energy of carbon dioxide gas at STP. We're going to need to know the temperature at STP, that's 0 degrees C. Add 273 to it, and you get 273 Kelvin. Okay, so 3 halves RT is our kinetic energy, subbing in those values, and we get 3,410 joules. It's got to be joules because, I'm sorry, joules per mole. I should have written that a little bit better. We got joules per mole because that's what the units are. My mistake there. Moving on, we're going to do root mean square velocity of gases. The reason it's a root mean square, it has a square root in it, and again, it's going to be an average. Not all the gas particles are going to have the exact same speed, same velocity. So we're going to talk about the average of it. Because we can get this out of kinetic energy, which is 1/2 mv squared. The mass is going to relate to a molar mass, to the moles of a gas. All right, if we're dealing with 1 mole of a gas, it's going to have so many grams, from the molar mass. Well, kinetic energy is in joules, and a joule is a Newton meter. I'm going to do this quickly. A joule is a Newton meter. A Newton is a unit of force, which is kilograms meters per second squared. All right, so that means we're going to have kilograms meters squared per second squared. Okay, so if we can get rid of the kilograms, we can have meters per second in there. And, well, that means we got to have kilograms, which means our molar mass has to be in kilograms per mole, not gram per mole. That's probably the most common mistake my students make on these problems. They do everything right, but they forget about that. And you don't have to know this too much, but it helps you realize, hey, I'm dealing with joules, which means I got kilograms as my base unit, which means my molar mass better be in kilograms. Otherwise, I have this factor of 1,000 in there that I'm going to take the square root of. All right. But anyway, root mean square velocity is this funky little equation. Alrighty, it's 3RT over the molar mass to the half. If you take a square root of it, technically you only have a positive root. I'm raising it to the half power to just clean up the equation a little bit. We're not going to take the negative root of that half power because we're not going to have a negative velocity. We're just going to have a positive velocity of all the gases. So 3RT over the molar mass, take the square root of it and you'll be good to go. As an example problem, what's the root mean square velocity of carbon dioxide gas? We just calculated its kinetic energy earlier. Here we got the root mean square velocity. So you got URMS 3RT over the molar mass to the half power. Plugging in your data, you're good to go. Remember we're at STP already. Whoops, wrong thing. We're at STP, so 273 Kelvin. All right. If there is our conversion, 44.01 grams per mole became 0.04401 kilograms. It's not a big deal. Just move the decimal place 3 and you're good to go. And then basically it's just a math problem from there. And you get 393 meters per second. Where does the meters come from? Well, if I was a crappy teacher, I'd say, well, it's velocity, so it must be meters per second. It's because if you deal with the joules per mole Kelvin, the joules here, that joules gives us our meters per second. We take the square root of it. Because remember, the joules was a kilogram meters per second squared. Okay, and it ends up being, Newton was that meters squared per second squared. We have kilograms per mole down below. For the temperature, we got Kelvin, okay? So over here we got our Kelvin, oh my God, Kelvin mole, forgot about that. Anyway, that's not working very well. If you look in here, Kelvin cancels Kelvin, moles cancels moles, and now there's joules and kilogram. The kilogram cancels the kilogram, and you're left with this meter squared per second squared tucked away in there. And you're taking the square root of it, so it becomes meters per second. Most of my students memorize that it's velocity meters per second. Okay, and I really don't blame you. For Graham's law relates to the diffusion of a gas. It's really common for questions related to the diffusion of gas, and technically diffusion is just the movement of gases from where they are to where they aren't. Diffusion is the passage of a gas through a narrow opening. So they're related, but not really, they're not the same thing. Okay. Graham's law is basically just a ratio. The smaller, more nimble gas, so to speak, the smaller gas should effuse more quickly. It just makes sense. So the rates of effusion should be opposite. This bigger guy will effuse more slowly, smaller guys will effuse more quickly, given the fact that they're both at the same temperature, so they have the same amounts of energy. Alrighty, so you can derive it out of the root mean squared velocities, alrighty, that we have right there. Root mean squared velocity, oh my gosh, this new thing is killing me. Root mean squared velocity ratios, and then we simplify root mean squared velocity to root mean squared velocity is basically the two rates, rate 1 to rate 2. If you do the math on the other side of the ledger here, you end up with it molar mass of 2 over 1. So if you're as a student, you really want to know this equation and memorize that, hey, they're opposites. Rate 1 to 2, molar mass 2 to 1, take the square root. Okay, that's the main way you're going to sort of mess up. It's not like a combined gas law problem or something like that, where you got V1 over T1 equals V2 over T2. The 1s and 2 have to flip on the other side, and that's why it's kind of nice to sort of know where they're coming from. The molar masses are on the bottom of that fraction, so they will flip. As a groovy little example, let's look at the rates of effusion of two gases. You have an unknown gas that's at 34 milliliters per minute. I really hate that color, so I'm going to bag that and see something a little bit better. 34 milliliters per minute. Methane is at 53 millimeters per minute. Determine the molar mass of the unknown gas. So basically, you got a rate, you got another rate, and you got methane. And so if you know methane is CH4, you should have a molar mass of that. So you know you're doing Graham's law. How do you know you're doing Graham's law? Because you're talking about rates of effusion. Okay, rates of effusion mean you got Graham's law. All right, so write down Graham's law. I wrote methane to unknown, unknown to methane. I wrote the ratios that way because I know I'm going to solve for the molar mass of unknown gas. I put it on top. If you wrote it in the reverse order, no big deal. It's different math. That's all. So I did my algebra and solved. My molar mass of methane is the 16.05. That's this guy right there already. I don't know why I went back to that color that I hate. And then my ratio of methane to the rate of the unknown. Alrighty. If you're caught up in the algebra, we had a half power here, so we squared both sides, which is why you got a square term there. And then that dude moved up. But at any rate, you do the happy little math there, and you get 39 grams per mole is your molar mass of your unknown. So to summarize, we had three guys. Kinetic energy, which is kind of straightforward, 3 has RT. A little bit more complicated with the root mean square velocities. Remember, molar mass is being kilograms. Then when Graham's law, we're doing some ratios. And don't get too caught up with the exponent. It's not so bad. I'm Dr. Mandis. You have yourself a great day. I'll talk to you later.